So what we have covered as of last week is about wave equation, and maybe you can recall three properties when we deal with wave equation using D'Alembert's method. The property one is that you have a domain of dependence, or the solution is based on a dependent triangle. So you can look for a backward triangle at any point in your domain xy point. You go for two characteristics and then draw a triangle, go to the base of the characteristics, and then you get the construct the D'Alembert solution. Second property is that if you take a single point on the initial line or any initial point, or any particular point, does not have to be initial, any particular point if you look at, and then look forward, you will find a forward triangle. You can draw two characteristics passing through this point and find a forward triangle. The solution inside this triangle is dependent on this point. So that point influence the solution in that region. And third point is the energy. So this is something perhaps we need to somehow either keep in mind, because we don't memorize mathematics. 2 plus 2 equals 4. I don't say we memorize that, but we know it, right? The same way we know wave equation, heat equation. We just don't memorize it, but we know it. So similarly, the energy of wave equation is very similar. Wave equation is partial derivative 2 of u partial with respect to t. You take this du dt, square it. Just think of in your mind, you are just changing the, putting the 2 into the wrong place, which becomes the right place now. And then you have the energy. So the energy is a powerful content that you can show that the energy is constant in some case and not constant in some case. So by knowing whether energy is constant, we can say something, but this is a kind of quantity, very important quantity for wave equation. So we have discussed a little bit, and we will perhaps be going through. So now this week and today's lecture, today perhaps we will be just looking at heat equation, but I'm not separating discussion heat equation versus wave equation, or separable method versus a characteristic method. Rather, I am grouping the content in a slightly different way. So I'm going to look at today about the effect of boundary condition. And this applies to wave equation and heat equation simultaneously, or perhaps any partial differential equation. So if we look at heat equation, so if I write down first heat equation, so this time I have added an additional term Q, and which by bracket xt, which indicates that Q depends on x and t. X and t are independent variable, which is not dependent on the dependent variable. That's the important point. The key concept in homogeneous equation and non-homogeneous equation. If Q is dependent on U, then this term could be considered a part of the operator. So that does not have to be a non-homogeneous. That still could be a source dependent on dependent variable. So this Q term we will call this is a source. So source means you imagine that a rod is continuously heated and that is time dependent. And then I will use the boundary condition. And I'll use an operator R to indicate that the boundary condition could be a Robin boundary condition. It could be a frozen condition. U at x equal to 0 is something, well, when A is 0 is a frozen condition, but when A is not 0, maybe it is heating condition, or it could be a derivative boundary condition. So that is what I indicate by R. So R indicates a Robin condition. So maybe it could be either U A of t or U prime 0, or could be a linear combination of U and U prime. And then you have a initial condition ux0. So what is new here? If we had q equals 0, a equals 0, b equals 0, then what you would do? You would just go ahead and use separation of variable, and you could find a solution. And you could use separation of variable and you would perhaps get a generic solution of this form, right? Yep. And of course, if I had u of 0, t equals 0, and u of L, t equals 0, the frozen condition. So the Robin condition now becomes a frozen condition. Then I have sign. If I have insulated condition, then I could have a cause, and so on. So that is what we know, right? Then we ask ourselves what we can do now if I have a source term, right? So before talking about that, I also like to mention about wave equation simultaneously. So for the wave equation, I will have a source term, could be a Q or F, it doesn't matter. U sub t x0 is gx. So that's fine. But now I have one more condition here. Maybe I can write here. U0 t equals h of t, and either x is greater than 0 or equal to 0, or x is less than or equal to 0. So remember, I just said that the solution is dependent on a backward cone at any point. So if your t increases, then the support, the cone increases. It goes from minus infinity to infinity. So that is broken here. I'm saying that I will introduce a boundary condition at some point, and then I will look at the wave either on the right side or on the left side. This is one modification. Second modification is I have a source term on the right hand side of this equation. So this is something we have already discussed, but it helps to repeat that today. So now I will say if f equals 0 and x going from minus infinity to infinity, we use D'Alembert's solution. So last week I have posted example in the lecture note, but I have really did not show you how to deal with that. You can perhaps look at also the textbook. There is an example. So that is something kind of self-learning. But at some point, I'll bring some examples. I don't think only just following examples and looking at something similar examples is a good way of learning. So let's first see if you can have the concept when we use D'Alembert's solution, and then something is broken that I put a right hand side. How to deal with that? I have given an example. Now I break another condition. Instead of x going from minus infinity to infinity, I give you half of that and give you a condition. And I did not explain how to handle that. I did not show you. So I say, okay, so the idea would be maybe kind of you want to put the solution from minus infinity to infinity, or use some trick or brainstorming, look at the book, and at some point I will provide some more concrete example. Okay, clear? So let's now look at the heat equation, because the techniques are similar, only the application is different. So we'll first say something, maybe a remark or a definition or just a hint. Question? T or yeah, yeah. So this condition we did not have before. We had the condition, two condition, u x0 is f, u sub t x0 is g. So x going from minus infinity to infinity. So now I'm breaking the domain. I'm taking either from x equal to 0 all the half portion, right half, or x equal to 0 all the left half. So then because of cutting the domain, I need an additional condition, which is u0 t equal to some ht. Is that clear? Yeah, and also we are for those equations, even if we don't mention t is positive. T is a time, so time, we don't have a time machine to go backward. Time is always positive. Okay, so something we call steady state of heat means So if I have a solution, maybe we have a simple solution here. You can look at that. And then think of what I'm saying here, steady state of heat, or here mathematically that is the solution. Okay. So steady state of the solution. So you look at here, k is a positive number, n square pi square by l square positive number. So t goes to 0, this term will be small, and then everything can just vanish. Everything can just vanish. But now, if I am hitting the rod, maybe I am hitting on the left hand and the right hand at the same rate. So heat, initially I had very high heat at the center of the rod, and then it decreases. So heat will be diffused. So I am hitting in both hand, heat will be diffused. Hitting in both end, heat will be diffused. So at some point there could be an equilibrium. That the more I heat, I wait, is maybe 20 degree. So you see that you in the morning, maybe at night you were out, your heater was off at home. So you go home, turn on your heater, and after some time, that's a good condition, good example. After some time, the temperature reaches a steady state and the heater shuts off. Right? So that is the steady state. So in this case, we look for whether we can find a steady solution or not. So the question, and the idea extends equivalently in other equations. So in heat equation, you think of, can I have a steady solution? And let's uh, do it with some examples. So definitely, if I have a source term time dependent and the boundary condition time dependent, finding a steady solution might be a challenging. So a good idea would be, maybe I can write here, maybe take q of x, a, b instead of q of x t, a of t, and b of t. So which means the idea I am demonstrating is still immature. It's a good, powerful idea, but still not very good if I have the source term time dependent. So that's one point to keep in mind. Okay, so let's demonstrate this with an easy example. So I'm going to set Q exactly 0. I don't want a source term. Rather, I'm going to put a non-zero term for the boundary condition, and I'm going to use a frozen or Dirichlet boundary condition. F of x is also arbitrary. A, B could be 1, 2, 3, 4, 5, 0, 1 million, 2 million, doesn't matter. Of course, too large may be problematic, right? So any reasonable number greater than 0. Okay, so we start for a steady solution. So maybe it's B, and steady which does not depend on time, so I will just take B. So Bx, it does not depend on time, it is a solution. So substitute back into the PDE. So replace everywhere you see in the system, replace with V. So dV dt equals k d square V dx square. Immediately you see that 0 equals k d square V dx square. Let's do one at a time. So we'll come back to the boundary condition. I see something, it is in a state that maybe I can solve it. Once I put that, I can see that it is just 0 on the left hand side. I can cancel out k. I can rewrite it d square V dx square is 0. And this is something I can integrate. So if I integrate, maybe I get a constant C1 and integrate again. So if you had a right hand side q independent of time, you would get d square V dx square equals maybe x. It is a x dependent, and you could still solve it. So we don't need more explanation. The same thing works if I have a q non-zero, but the only thing is q has to be a function of x only. Then we can easily solve it. Now I go to the boundary condition. So instead of u, I replace V, and it does not depend on t, which is A, and put back to the solution C1 times 0 plus C2. So this gives me C2 equals A. I found one constant. Then I go BL equals B C1 L plus A, which implies C1 equals B minus A divided by L. I have found a steady solution. So when I found the steady solution, I made a mistake. I lost something. So I try to recover that. And that loss, because it's a linear equation, so the loss is linear. So remember, we can't apply this to directly this way to nonlinear equation. There might be possible, but you need to be careful. But as of now, we are looking for linear equation. Okay. So define a new variable wxt, which is the difference between u, or you can say I have a solution uxt which equals vx plus, so we'll call this part vx is a steady part, and then we will have another time dependent part. Often we call it transient part, a steady part and a transient part. So I will substitute back everything to heat equation. So I can say, okay, Wx, I'll replace U with Wx if I assume in this form, or if I look at in this form, I will set everything on the right hand side to the heat equation. So maybe I do that. So I will say, okay, d dt u, so which is v plus d dt w. On the right hand side will be k d square v dx square plus k d square w dx square. So if I look at in this expression, it will be the same thing if you look at in this expression with just a plus sign and minus sign. And I know that this first term is 0 because v is not dependent on time. And already I have said earlier d square v dx square, this term is 0. So I have not a big change. I had an equation with u. I have written the same equation in terms of w, just a change of symbol. But if I had a right hand side, this time the right hand side would have been gone. So I would get a homogeneous equation if I had a non-homogeneous equation. But now look at the power of the method for boundary condition. So the boundary condition is u at 0 t is this guy. So the boundary condition would be v at 0 plus w at 0 t, which equals a. So that turns out v solution is known, right? So if, well, I have already said v at 0 equal to a. Now u at 0 is also equal to a. So you will get confused, but let's look at here. If you substitute x equals 0, it is c2 and c2 is a. So this one is a. So I get a plus w0 t is a. So I get w0 t equals 0. Let's put box into the equation that I need. Then I go for the next condition, v at L plus w at Lt equals b. So v at L would be C1L plus WL t equals b. So C1 is this quantity. So v at L is also, which is I have here, v at L I have calculated earlier. So maybe I can just reuse that. You can just reuse that calculation. V at L is also b. We could substitute C1 and C2 and we can come up with the same thing. So I will have WL T is 0. So I have a homogeneous equation. So I have ended up and I know how to solve a homogeneous equation. Now I can solve that. But that's the trick. You keep in mind solving non-homogeneous heat equation. All you have to keep in mind that the equation can have a source term which is dependent on x, and the equation have non-zero boundary condition which are independent of time. And then you can find a steady solution and arrive at a homogeneous problem. A homogeneous problem, just to refresh our knowledge, let's just quickly do that. Separation of variables. So you substitute s of x e to the power minus lambda t. There is a k missing, I'm sorry. I have here k and I forgot to write down k. If I substitute back here, then I can see that minus lambda s e to the power minus lambda t is k s double prime e to the power minus lambda t, and then I get s double prime equals k over lambda s. And I have s of 0 is 0, s of L is 0. I have the boundary condition. And this is the simplest stage of separation of variable. Linear heat equation with homogeneous boundary condition. The eigenfunctions are sines or cosines. Will that be sine or cosine in this case, or a mixture? Eigenfunction s and x will be sine or cosine, or why sine or cosine? Yeah, so that tells me sine. So it tells me sine. If you still are not comfortable with that, maybe it's a good idea to just review how we solve this second order ODE using this boundary condition. So characteristic equation is m square equals k over lambda. I'm missing a minus sign here, sorry. So that is a minus sign. Yeah. Without the minus sign, I cannot get sign. So I'll have to have the second order ODE in this form, a second derivative on the left hand side, and the right hand side a negative quantity times the dependent variable. So I have k positive, lambda positive, I have a minus sign. So it's a negative. So I take the square root, then I get e to the power I theta, which is sine and cosine, which gives me sine and cosine, right? So my solution is, and I have also found what is k by lambda. K over lambda is square root of k over lambda is n pi over L. So solution u of x t 1 to infinity a n sine n pi x over L e to the power minus k lambda. So from here lambda is I think something, yeah, something wrong. What is wrong? There is a typo. Well, that's one. You found one, but that's not a major one. You see how the TAs work. So you make a mistake, and TAs are paid very little to find your mistake. Sometimes they don't find your mistake. And how I mark your exam. So I made a mistake. Okay, so this one here should be lambda over k or k over lambda? Lambda over k or k over lambda? Lambda over k. And of course, this is W. Okay. So lambda is k times n square pi square over L square. N square pi square over L square. And then use initial condition. So what is the initial condition? If you go back here or look back here, so the initial condition would be W at x t0 would be U at x t0 minus the steady state. So minus the steady state. So this is something maybe I know some of you might be confused. So let us do one more step. So what I see is that now initial condition, I subtract the steady state solution from the initial condition. And this is something can be done very much once you are familiar with, can be done using mental math, very much like U substitution we do in calculus. And if you look at homework problem number 1, is a very similar way. You can think of all you have in your mind. I have my heat equation which has source term or boundary condition source term time independent, constant in boundary condition, x dependent in equation, and I want to look for a substitution. And the substitution idea would be actually I'm looking for a steady state solution. So you can have mental math to solve for the steady state solution and you get the substitution, or you work it out. Okay, so what's next? Use orthogonality. And we are done. I just have not written down the solution. I left it with you. So you can come up with another quick example. Let's just repeat this problem. And this time again, I am not using anything on the right hand side, that I leave for you as my strategy. I don't give all the examples, that you just use plug and play, take an example and solve. Following the example, solve another one. Rather, these are examples how to deal with non-homogeneous terms, but no example is given so far. A non-homogeneous term in the equation. The non-homogeneous terms are coming in the boundary condition. What is the change here? So all I have changed is this condition. So maybe just change the color. Everything else is same and non-homogeneous. So what we do is we look for a steady, find steady state. And that I just have shown how to do that. You can find it. That will definitely be V of x equals C1x plus C2. So once you have found the steady state, solve Make sense? Doable? I'm sure if I let any of you come forward and solve it in the board, you can do it. But since I have short of time, so I don't want to repeat everything. So it is finding the steady state solution. Very much I have shown here. You can find the constants C1 and C2 by using the boundary condition. I think all I want to just explore as a hint about the eigenfunction and eigenvalues. So I will take W equals S of x e to the power minus lambda t, and I'm going to consider lambda is positive. So then I have minus lambda s e to the power minus lambda t equals k s double prime e to the power minus lambda t. And there is chance of mistake. I have already made a mistake when I wrote last time. So maybe you write down in two steps. So you can see it. Lambda over k s of x, and lambda over k is positive because I'm starting with lambda positive and given to me in heat equation k positive. When I divide lambda positive number by k another positive number, I get a positive number. So I get a characteristic equation for this ODE. So to solve this ODE problem, I get a characteristic equation which is imaginary. Characteristic equation has a solution square root of minus lambda by k. So the solution will be s of x will be a constant, maybe C3 cos square root of lambda over k x plus C4 sine square root of lambda over k x. So, well, since I'm showing you the ODE part, maybe I also show you how you find the characteristic equation. So, characteristic equation, you look at the differential equation second derivative, m square equals minus lambda over k, m equals plus or minus square root of lambda over k. Right. So purely imaginary solution for the characteristic equation or purely imaginary eigenvalue of this second order ODE. So I have sines and cosines, and then I have S of 0, which is C3 times 1, cos 0 is 1, plus C4 times 0, and S of 0 equals 0. Right. So what I get here C3 is 0. C3 is 0. Then I calculate S prime x, which is now C4 times C3 is 0, so the first term is gone, and that tells me that the solution is sine. And this is something we can use. We should be able to do it in mental math, because we are busy person. We don't need to write down everything. But I say when you get a question, show your working. That doesn't mean everything. Mean working. So C4 square root of lambda over k cos square root of lambda over k x. Then you get S prime 0 equals, sorry, S prime L. I'm sorry. This condition is at S prime L. So I get C4 square root of lambda over k and cos square root of lambda over k L equals 0. So the coefficients are not 0, because otherwise you will get a trivial solution. That is what we don't want. And this equals what? Who can tell me? In terms of cos or sine? Of course, left hand side, my eigenfunctions are sine, but here I have a cos. So I have to find something cos. I know cos pi by 2 is 0. But then cos 2 pi by 2 is cos pi, which is minus 1. Cos 3 pi by 2 is 0. Cos 4 pi by 2 is 1. Cos 5 pi by 2 is 0. Cos 6 pi by 2 is minus 1. So 0, minus 1, 0, 1, 0, minus 1, 0, 1. So odd multiple of pi by 2 gives me a 0. So I'll say 2n plus 1. A odd number 2n plus 1, which is always odd, pi by 2. So I want lambda. So I have found lambda, I have found my eigenfunction. The solution Wx t, and this time I see that this lambda is working from n equals 0 up to infinity. N equals 0 up to infinity. So I'll write my sum, n from 0 up to infinity, a n cos of 2n plus 1 by 2 pi x e to the power minus k 2n plus 1 square I square by 4 times t. Yeah, L should go to the right hand side. Thank you. n, yeah, L n squared.